Okay, I'm back, and even though you didn't know I was gone, and what I've done here, I'm pointing, and I'll take pictures and show you. What I did was kind of expanded this guy's little switch thing idea and added it to the switches that you have to cut here at some point. I'm not ready to cut them yet, but and then you can do what you need to do to make these things stay. And you have switches there. You can open and close and so forth. And soldering is. And what I did here is I've got one of these little double connectors you can get for a couple of bucks, and I put the other half of it on a just a 12 volt. Basically, it's a I guess you call it a motorcycle battery, but it's a sealed one, and it's more of a burglar alarm battery. And now I can just sort of plug my battery in when I choose to and unplug it, and you could put a switch in this wire if you wanted to. In some cases, I've put switches here just sort of as a battery master switch. You could put a battery master switch in the ground. I've done that before, just soldered in a switch for the battery master. It's really entirely up to you. I want you guys to feel comfortable experimenting. And before we move on, what I want to do is I want to show you what happens when you blow the fuse, which is the this piece of solder that I put here. So what I'm going to do is I'm going to fix this just because it's the easiest thing to do. No, you know what I'm going to do? Yeah, I'm going to do that. Change my mind again. Yes, that is what I'm going to do. One of the things that I did beforehand is I've got a little piece of steel wool here, or you can use Scotch-Brite or whatever. And if you need to, sometimes you can polish this up a little bit and it'll solder way easier. Okay, but what I'm going to do is I'm going to solder this back together, then I'll cut it again. And I'm doing that because I want to show you how this fuse blows. If you haven't done it yet, you might be interested in seeing that. So I will take this and I will solder a little bit of a blob on the left and a little bit of a blob on the right, and then join them. And now that little cut point for the switch is, or for the resistor, is now closed. So I have a direct short coming in the positive wire, coming down, going through the fuse, no resistance there, 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 and that. So if we do Ohm's law, what you'll see is if I take 12 volts, for example, and divide that by 0, you get error. And that's because division by 0 is impossible. And I can use some number that's just slightly larger than 0. So if I do 12 divided by 0.000000001, then the current flow is 12 quadrillion amps. Okay, of course the battery can't maintain that, but that's how the math works. So the current goes up very, very quickly when you hit a short. So you need to be looking right here, and if this works the way I want it to work, then in just a couple of seconds you're going to see something kind of fun. Okay, so the fuse popped. So this actually does work. It works really well. So let me do this first to make sure that I'm doing it right. Cut this back open. Okay. Okay, that's good. Got it open. A little tough. Yeah, it's open. Okay. All right. So now I can repair my fuse. It'll just pop off and just pop off. And the resin gets kind of sticky. Cut yourself a little piece of solder. Solder that back in. If you kind of push it a little bit, it tends to work a little bit better. And do that. And sure enough, we have a new fuse. Okay, so you can make it look like a fuse, or you can not, or whatever. Okay, that's the fuse symbol right there. Okay, that's the fuse symbol, so whatever you want to do. All right, so here's what I'm going to do. I've got my amp meter set up, or I will. But I'm going to show you how this works. Because I said a minute ago that if you combine all these resistors, then when you combine them, it's as if it's just one series path. Okay? And when we did it, we came up with 54.9 ohms. So I guess I can correct that. I'm going to sharpen my pencil here. 54.9 ohms, and this was actually 54.9. Do not be afraid to draw on these things. I mean, that's kind of why I did it. I want you to draw on it. I want you to, you know. So what do I mean when I say that it becomes a series path? In reality, what's happening here, and this is like my, bucket example here. If I were to draw a bucket, what you'll see is, here's the bucket. Okay? And it's full of, whatever. Well, if I drill a hole in the bottom of the bucket that's, say, a 1/4 inch, then a certain amount of water will flow out, right? And then if I drill one that's a 1/2 inch, then it's a bigger hole, but the bigger hole has less resistance, so more current flows. All right, and then lastly, if I drill a bigger hole that's 1 inch-ish, then now I've got water pouring out big time, okay? Well, here's the weird thing. This has higher flow because it has a smaller resistance. This has a smaller flow because it has a bigger resistance. That's resistance. That's the relationship with resistance. But if you added up those three flows would be more in total than any of them by themselves. So if I put a catch basin here and I started to catch the fluid, then the total amount of flow would be equal to this plus this equals total, right? Doesn't that make sense? Well, here's the first mistake in most books, and make sure you understand the mistake. The phrase, current takes the path of least resistance, is technically not correct. It's mostly correct, but it's not correct because of this relationship. Most current takes the path of least resistance. And that's because of the teeter-totter. That's because of this teeter-totter, okay? So more resistance is less current, okay? Well, less resistance is more current. So the whole thing kind of does this, teeter-totter, okay? And the peculiar thing is the more resistors you add in parallel, the lower the resistance gets. Well, we proved it. One resistor by itself in parallel was 100. Then we put in the 330 and it dropped to like 70-something. And then we put in the 390 and it dropped to 60-something. And then finally we put in the 470 and it dropped to 50-something. So the more paths we provided, the greater the total flow. And according to Ohm's law, volts and ohms make amps. That's the way you need to say it. Volts and ohms make amps. More of this is more of this. More of this is less of this. Well, one of the critical things to understand about resistance in parallel is you have to be isolated. because if you're not isolated, you don't get the right answer. Well, I can prove that very quickly by just showing you that anywhere I read the resistance of this set of current paths, I get the same number. So I can put it here and here, and I get 55. I can put it here and here, and I get 55. I can put it here and here, and I get 55. I can put it here and here, and I get 55. If I put it here and here, I get 55. If I put it all the way down here and all the way up here, I get 55. And even more interestingly, if I take the battery cables, this is this would be in the vehicle, this would be the battery cables. Look, you can unplug the battery cables and you can read the resistance of a circuit from the battery cables. Well, why? Easy. The battery cables are part of the circuit because the circuit does this and comes back up here to the battery. Okay? So the battery cables are part of your circuit. The feeder, the fuse panel, the ground, all part of your circuit. Your circuit doesn't go from here to here. Your circuit goes from here all the way down here back. And I'm not saying that's current flow because you could say it goes this way as well. You know, my preference is negative flow, but I don't talk about flow, so I don't really care. All right, so what do I want to show you here? Well, I want to show you that, and I want you to understand that the value in knowing this is that if you work on equipment, if you don't take the time to unhook all of these systems and disconnect all the individual circuits, you will not get a correct answer, which is one of the reasons the ohm meter stinks as a diagnostic tool. Okay, so what am I going to do? Well, what I'm going to do is I'm going to set this up for amperage, and I'm going to show you how this math works real quick and show you what the meter is because I want to give you a little bit of meter reading. I want you to understand the amp meter, and I want you to understand this math just a little bit better. And I want you to understand what happens as we add paths in parallel. The flow goes up, but it goes up because the resistance goes down. Now, of course, but what I've got is I've got my amp meter, and I've got on the low amp scale. I'm going to put on the high amp scale because that's going to make these numbers match. Okay, so that's what I'm going to do. But when I move the red lead over, this meter becomes a jumper wire. Okay, and then I don't personally like teaching in terms of put the meter in series with this, put the meter in parallel with that, because I mean I could read voltage here and it's in series with the circuit. Or I could read voltage drop here and that would be in parallel with the load. So quite frankly, I am less enthused by that than some people are. I just want you to know how the meter works. And the meter on amps is a jumper wire, the same as a piece of wire you pull off of a spool on the wall in the shop. And when you use it as a jumper wire, it becomes a switch. So I've got a switch. Here's my switch. Got the amp meter hooked up. Do the math again here. 12 point... I'm going to use 12.6 this time because that's really what a battery would be maxed out. Divided by, hit that too, 97.3, and I get about 129, 0.129. Well, 0.129, 0.129 amps is equal to 129 milliamps. Okay, so I can read either on the amp scale or I can read on the milliamp scale. And right now I'm reading on the amp scale because the number that we get here is going to look really close to the number we get there. So let's see what we get. I think I've got it connected properly now. I think I've got all my fuses working. So I've got 0.129 as the calculation, and if I turn the switch on here, I get I know it's working. I'm trying to use this thing here. There we go. I guess that would help, huh? See, when I don't mind this happening, to be frank. People are going to slam the crap out of me, but I don't care. The point is, when you're involved in this stuff, you make mistakes, all right? But what you don't want to do is freak out. So I didn't get the number I expected. So what I'm trying to teach you is, if that's the number I expect and I don't get that number, then there's something wrong. And what was wrong here was I didn't have my meter set on 20 amps. I moved it here, but I didn't move it here. That's a mistake. Well, I calculated 0.129, and I'm getting about 0.13. That's as accurate as this is. All right, so let's see about the 330, which was actually 319. So that number is going to be even smaller. Disregard. 12.6 divided by 319.9, 319.9 equals 0.039 or 0.04. And if we turn this on, let's see if we get, it takes a few seconds to get these things all organized here. .04. Okay. Well, the reason I'm using the high amperage is because it's matching what the calculator is saying without having to do any thinking about it. But 0.04 amps is 40 milliamps. And I'll come back in a second and show you this. Now, the 330 and the 390 are not going to be much different. I'm going to be surprised if it drops below 0.03. So let's do 12.6 divided by 382 equals 0.032. So what I would possibly expect would be for this to run at about 0.03. And it's between 0.3 and 0.03 and 0.04. All right, well, the 470 is going to be even smaller because it's a much higher resistance, more resistance, less current. And over 5 is divided by 2, so we're expecting about 0.24, so I'm going to say maybe 0.25, 0.26, but we're going to get a very bad reading here, and I'll show you this in a second. So if we do 12.6 divided by 460, 0.027 or 0.03, which means we're going to get basically the exact same number, probably. And we get 0.03. All right, well, so this one was 0.130, this one was 0.04, this was 0.03, and this was 0.02. So let's see what it looks like in the milliamp meter. We'll put this down here to milliamps. This time I'll remember to move the dial. And if I turn them on, this one was 0.130 on the big scale, but it's 124, which is close. This one I believe was 0.038 or 0.036 or something like that, and there's 38 milliamps, which is what I expect. This one was 30 something and another 30 something, and sure enough that's what we got, 33.14. And then this one was lower, it's about 25, 26, and we get 27. Okay, so notice as the size of the resistor gets bigger, from 100 to 330 to 390 to 470, the individual circuit paths carry less current. Well, here's the way parallel works. We've already seen that if I measure the full resistance, it's 54.9 ohms. So what I can do is take my 12.6 divided by 54.9, and I get 0.2295 or 0.223 or 0.230, excuse me, which means this number on amps should read about 0.230 if I put them all together. So I put this one on, turn this one on, and then I'll turn this one on. So you can make switches any way you want. I'll turn this one on, and I'll turn this one on. And we get 0.23, and we calculated 0.23. Okay?